Okay, so let's discuss about the atomic or ionic movement in the materials. Okay, so what's the driving force to make the atoms or ions move? What's the driving force? Okay, and for this question, we have to realize how does diffusion occur? Okay, and why it is an important part of a processing, and how can the diffusion rate be predicted for some simple cases? Okay, and how does diffusion depend on structure and temperature? Right, previously we already learned about those defects, the point defect, linear defect, error defect, and so on. And those defects are highly related to the diffusion process. Okay, is highly correlated to diffusion process. Okay, so the definition of diffusion is mass transport by atomic or ionic motion, and its mechanisms including what? Including the random motion, or we say it's a Brownian motion. Okay, if they are gases and liquids. Okay, what we already mentioned previously are solid, right? The solid defect, the defect in those solids, and diffusion dominates those point defects or linear defect in solid materials. Okay. So first we look at the interdiffusion. In alloy, atoms tend to migrate from regions of high concentration to regions of low concentration. Okay, for example, initially we have two types of metals tightly contact with each other. Okay, and after sometimes the atoms start to move, to diffuse through with each other, right? From the high concentration to the low concentration. For example, if the one side is nickel and the other side is copper. Yeah, for example, this side is copper rich, right? And this side is nickel rich. After sometimes the copper atoms moves from high concentration to low concentration, right? And the nickel atoms from its high concentration region to low concentration. Sorry, it's nickel. Okay, therefore the concentration profile change within the interface. Okay, within the interface between nickel and copper. Okay, and also the vacancy diffusion is accompanied, and the vacancy diffusion is atoms exchange with vacancies. Okay, or you can call it a pair. It's the atom and vacancy pair move. Okay, and the vacancy diffusion applies to substitutional impurities atoms, and the diffusion rates depends on the number of vacancy and the activation energy to exchange, right? So if there is a vacuum side and the lattice atom will move to this vacuum side, and its original spot is empty, and the neighbor atoms will fill in this empty vacancy and keep going. Okay, and usually those interdiffusion is accompanied by vacancy diffusion and self-diffusion, and the diffusion between two metals. Okay, Therefore, you can look at the metal alloy, right? So this side is copper rich and this side is nickel rich. And also they have the vacuum sites in each part, right? Right? You have the vacuum side in each part. Therefore, it's a combination diffusion, or say a combination of interdiffusion. Okay, combination of interdiffusion because you have the vacuum diffusion, okay, and probably have a self-diffusion. Okay, self-diffusion. It's those diffusions occur simultaneously. Okay, and finally, this diffusion will achieve a equilibrium state. Okay, this diffusion will achieve an equilibrium play, right? After the diffusion process complete. Okay. Yeah, that's why I already mentioned previously. It's called the self-diffusion. That's mean the in an element solid atom also migrate, okay, between each lattice point. Okay, and also this diffusion within the interstitial site. Okay, it's called interstitial diffusion. Okay, that means the smaller atoms can diffuse between atoms. Okay, so you can see we have alloy, we have impurity, or we have impurity atom, which is usually smaller than those lattice atom, and it can move around, okay, within those interstitial sites. Okay, can move around between atoms and within those interstitial sites. Okay, give an example of the hardening case. Okay, diffuse carbon atoms into the host iron atoms at the surface. Okay, this process can strengthen the surface strengthen. Okay, surface strengthen by those carbon diffusion. And this carbon diffusion is an example of interstitial diffusion. Okay, and the presence of carbon atoms makes iron harder, or the carbon steel. Okay, the carbon diffused to the iron to form a steel. Okay, so of course, the gear body, for example, we have a gears, right? The gear body should have enough strength, right? However, when we use to transmit power, okay, the contact point between each gear, this contact point or this contact surface should has very strong hardness on its surface, okay, for transmitting this power. Okay, because the wearing will happen between the surface, right? Between the surface. Okay, therefore the main parts to be strengthened should be the surface. Okay, so it totally depends on what your application is. For example, for your iPhone cases, what's the importance? What's the strength? Which part should be strength of your iPhone cases? You can think of these questions because you're not gonna throw your iPhone, right? You're not gonna use your iPhone as a weapon, right? To fight with somebody, right? It's impossible. You won't do that. However, maybe sometimes you are very uncareful, or you're careless to scratch your iPhone, maybe to indent your iPhone, okay, to hit your iPhone suddenly, okay, you doesn't mean to do it, right? You doesn't mean to do it, okay. Therefore, what's the importance of the iPhone cases? It's the surface hardness, but not the body strength, right? But not the body strength. Okay. And let's look at the other example is a semiconductor. If you want a specific region of the silicon wafer are p-type rich or n-type rich, right? We can diffuse the group 3 or group 5 elements, right, by different technique such as the sputtering process or the evaporation process or the e-beam process. Okay, no matter what, we can deposit those p-rich or n-rich elements on the surface of a silicon wafer, and we heat it up and we heat it up, and those elements we coated on the silicon wafer will diffuse through the specific region, okay, to modify its conductivity, okay, to modify its conductivity. Okay, the temperature, when the temperature increases, what's going to happen of the diffusion process? The temperature increases, the ability of the atom or ion to diffuse, right? Temperature increases the ability of atom or ions to diffuse. Okay, as we mentioned the temperature, okay, the temperature change, we must think of the relation of the movement rate to the temperature, and that is dominated by the Arrhenius equation that we already mentioned in previous chapter, right? The concentration of vacancies, right? How to evaluate the activation energy, right? We also use the Arrhenius equation. Now it's the rate, it's a diffusion rate, I'm sorry. The diffusion rate, okay? The diffusion rate is equal to exponential function. Here, Q is also the activation energy to trigger this the diffusion process occur, right? And R is the gas constant. D is the temperature in temperature K, Kelvin, right? And C naught is a constant. Okay, it's a constant we need to solve. If we take the nature log from both sides, we are gonna convert this exponential function into a linear function, right? We'll convert this exponential function to linear function, right? It's a linear function, right? Okay, so there's an example. You can just review it. It's not too difficult. You just plug in some numbers. You can manipulate. You can look at this process. Okay, so we can convert it from the previous example. We can convert it, this exponential function into a linear relation, right? And we can plot a linear function. Can plot the linear function. Okay, and the slope. Okay, the slope of this linear function is what? It's minus R over Q, right? R is the activation energy. Sorry, Q is the activation energy. R is the gas constant. Okay, therefore we can evaluate activation energy for this diffusion process, right? Also, we can figure out the intercept right here. Okay, we can figure out the intercept of this linear function, right? Right, you can find this intercept of this linear function to figure out the nature log of C naught of xenon, right? And a diffusion atoms must be squeezed past another atoms to reach a new position, and which requires activation energy. Okay, a low activation energy indicates easy to diffuse, right? Easy to diffuse. So one obvious example is the temperature. Okay, some diffusion can occur at low temperature. Okay, and some diffusion processes need very high temperature, high elevated temperature to trigger this diffusion process. Okay, and generally the interstitial atoms require lower activation energy than the substitutional atoms. Okay, so from this figure, you can find the substitutional atoms because it is smaller than those lattice atoms, right? And it is smaller, and its movement is among those interstitial sites. Just move within those rooms, move within those space, right? Therefore, the activation energy, the requirement of the activation energy is lower for interstitial diffusion. Okay. And for the vacancy diffusion or substitutional diffusion, which always need higher activation energy to trigger this diffusion process to occur. Okay, to occur. So you can see the activation energy of the substitutional or vacant diffusion is higher than that of the interstitial diffusion. Okay. Okay, so let's look at the diffusion rate. So we have to mention the Fick's first law, which relates the rate of diffusion that can be written in terms of flux J to the diffusivity D of the diffusion couple and the concentration gradient. So from this equation, what is the driving force for diffusion? What's the driving force for diffusion? Okay, what is the driving force for diffusion? So from this equation, we can realize that the driving force is this term, right? Because this is a constant, the diffusion coefficient, and this is a constant, and this is the driving force. So what is this? It's the concentration gradient. Okay, it's a concentration gradient. And Fick's law is deal with steady state diffusion. So what it means steady state? Okay, steady state is not just for diffusion, but in different process, scientific process. For example, like heat transfer. Okay, heat transfer or dynamic system, and so on. Okay, so the steady state means that what the time is independent of this process. Okay, of this diffusion process, time is independent. Okay, so we only discuss about its steady state. Okay, we only discuss about its steady state. Okay. Therefore, the concentration gradient acts as the thermodynamic driving force for diffusion that were already mentioned previously, right? And the concentration gradient shows how the composition of materials varies with distance. It might be created due to what? The two different materials contacting, right? The interface between two different materials and the fluid contact solid. Okay, we already discussed the two types of metals contact with each other, right? but maybe the diffusion occur between fluid and solid, fluid and fluid. Well, it depends on what kind of materials contact with each other, right? And it must, during this diffusion process, its internal must be non-equilibrium, okay? Must be non-equilibrium. Of course, there are many other sources, okay? There are many other sources that emphasis on the diffusion process, okay? Okay, so one example of this steady state diffusion. For example, we have a sandwich structure. One layer is nickel, and the other layer is tantalum, and the interface, the barrier layer between these two metals is a magnesium oxide. Okay, and the surface area of each materials is 2 centimeter by 2 centimeter, and the thickness of the magnesium oxide barrier layer is about 0.05 centimeter. Okay, therefore, a 0.05 centimeter layer of a magnesium oxide is deposited between layers of nickel and the tantalum, right? And we put this sandwich structure at elevated temperature, about 1400 Celsius, and the nickel ions diffuse through the magnesium oxide to the tantalum layer. So determine the number of nickel ions pass through the magnesium oxide per second. Okay, at 1400 Celsius, the nickel lattice parameter is 3.6 times 10 to minus 8 centimeter, and the diffusion coefficient is 9 times 10 to minus 12 centimeter squared per second. Okay, so when we put this sandwich structure at 1400 Celsius, right? And this nickel will diffuse through this magnesium oxide to the other end of tantalum rich layer. Okay. Therefore, we can calculate the composition, the nickel composition as the 100% nickel at the nickel rich side, right? The nickel rich side. The nickel rich side means this side. Okay, at this interface. This interface, we assume this nickel atom is 100%. Okay, it's 100%. Okay, and the concentration per volume per unit cell is what? We know the nickel is FCC structure, therefore it has 4 nickel atoms in a unit cell, right? And we already tell you its lattice parameter is 3.6 times minus 8 centimeter, right? Therefore, we can calculate its composition or composition, a number of nickel atoms per volume per each unit cell, right? So it's 8.573 times 10 to 22 nickel atoms per centimeter cube. Is that clear? That's mean the concentration at this nickel layer, and the composition at the magnesium tantalum interface is 0% of nickel initially, right? Initially. Is that clear? Therefore, we can calculate the concentration gradient. So 0% of nickel minus 8 times 573 times 10 to 22 divided by the thickness of magnesium oxide layer is 0.05 centimeter, equals to minus 1.715 times 10 to 24 nickel atoms per centimeter cube. first order, okay, the first order, okay, and the flux of the nickel atoms through the magnesium layer, magnesium oxide layer, is the flux, right? The flux J equals minus D. D is the diffusion coefficient times the concentration gradient. Concentration gradient. So we already know the diffusion coefficient, which is a constant, equals to 10 to minus 12 times the concentration gradient is minus 1.715 times 10 to 24. Okay, equals to 1.543 times 10 to 13 nickel atoms per centimeter cube second. Okay, it's a flux. That's the rate, atom rate pass through per unit area, okay, per unit area. Therefore, if we times the area, the flux times the area, the area times the flux, J, we get a number of atoms per second, right, diffused through this barrier layer. Okay, therefore we can figure out it's about like 6.17 times 10 to 13 number of atoms per second. Okay, per second. And the volume of nickel move from the nickel magnesium oxide interface is what? Is what? We already know the rate of the rate of diffusion is about the 6.17 times 10 to 13 nickel atoms per second, right? And we times the reciprocal of this nickel magnesium concentration. So what's the definition? What's the meaning? Is the reciprocal of this, right? This reciprocal of the nickel composition. That's mean what? That's mean the volume of each nickel atoms, right? So you just take the reciprocal of this, right? Take the reciprocal of this. That's mean what? That's mean the volume of each nickel atoms, or we can say the volume of the nickel atoms pass through this barrier layer. Okay, so we have so many nickel atom, right? We have this number of nickel atom per each centimeter cube, right? Per centimeter cube, and we take the reciprocal of this. That's mean what? That's mean the volume of this number of nickel atoms, right? Therefore, what? This is the number of atoms per second, and this is the volume, right? The volume of 8.5 or 573 times 10 to 22 number of nickel atoms. Okay. Therefore, we can figure out what? We can figure out the volume of nickel atom removed from the nickel magnesium interface per second. Okay, per second. Right, so we can realize it from its units. Right, this is the volume. It's the volume of nickel atoms. Okay, it's the volume of nickel atoms. And the thickness by which the nickel layer is reduced per second is what? We just divided this number by the area 4 centimeter, right? 4 centimeter cube, 4 centimeter square. So we can get 1.8 times 10 to minus 10 centimeter per second. That's mean the thickness reduced, the thickness reduced, right? The thickness of nickel layer is reduced per second, okay, when the diffusion process occurs. Okay. And the factors affecting diffusion, right? What those factors? Of course, temperature and the diffusion coefficient. The diffusion kinetics are strongly temperature dependence, right? Temperature dependence. So we already look at this for several times, right? For several times. And the D is the diffusion coefficient equals to D naught. D naught is a pre-exponential times exponential is the minus Q divided by RT, Okay, the Q is the activation energy to trigger this diffusion process. R is the gas constant, and T is the absolute temperature in Kelvin. Okay, in Kelvin. Okay, so if we compare with the diffusion rate with different types, okay, the volume diffusion is the slowest one. That's mean the vacuum-C diffusion, the substitutional diffusion, or even the interstitial diffusion. Okay, they need very high activation energy to trigger this diffusion process occur. Okay, for the surface diffusion or grand boundary diffusion, only need very low activation energy to trigger this diffusion process. Okay. Therefore, we can compare. For example, for the thorium in tungsten, it's binary metals, right? It's binary metals. Two types of metals. Okay, and the diffusion, the activation energy is much higher than the surface diffusion, right? The surface diffusion, and the activation energy of this binary metal, or we call as the different types of metals diffusion, is higher than what? Is higher than silver in silver. That's mean two types metals are the same, right? And of course, for the same metals diffusion, is still that the volume diffusion rate is the volume diffusion activation energy is much higher than the surface diffusion. Okay, the surface diffusion. Okay, and the other factor is time. Diffusion requires times. Controlling diffusion time during the process can be the key to produce a uniform or unique property of microstructure. Okay, for example, the trench process. The trench process, that means we heat up the steel in a specific temperature, and we cooling down very quickly. Okay, very quickly. That means this time for diffusion is extremely short. It's extremely short, and we can make a very hard structure, metal structure or steel structure. Okay. And also, these diffusions depend on the bonding and the crystal structure. Okay, we already mentioned that the interstitial diffusion occurs faster than vacuum seal substitutional, and the close packed crystal structure has the higher activation energy, right? Of course, because the close packed crystal or the close packed structure has more atoms packed together. That means has higher bonding between atoms. That means we need a higher energy to break those bonds. Okay, to break those bonds or to trigger the diffusion process occur. Okay, and the cat ions diffuse faster than anions due to size. Okay, the cat ions has a smaller sizes than that of the anions, and also the ionic diffusion also transport charge and enable conductivity. Okay, one example is our lithium-ion battery, right? Lithium-ion battery. So during charge, when you plug in your cell phone, that means the lithium ions diffuse through this separator and the electrolyte to the anode, right? To the anode. And the electron will pass through from the outside circuits. Okay. And when you start to use your cell phone, the lithium ion will move from the anode to the cathode. The same thing happens, that the electron will pass through the outside external circuits. Okay, when you are using it. Okay. And the diffusion coefficient also depends on the concentration of diffusion species and the composition of the matrix. Okay, that's for sure. We already mentioned that the concentration gradient is the driving force, right, to trigger the diffusion process occur. So this figure just show you the diffusion coefficient corresponding to different type of steel and metal alloys. So, for example, the interstitial diffusion, which is the carbon in alpha iron or carbon atoms diffuse in the gamma iron. Okay. So this interstitial diffusion is faster than the substitutional diffusion. Okay, so this interstitial diffusion is much higher than the substitutional diffusion. Okay. So give you example. At 300 Celsius, the diffusion coefficient and the activation energy for copper in silicon are D equals to 7.8 times 10 to minus 11 meter square per second, and the activation energy equals to 41.5 kilojoule per mole. And what is the diffusion coefficient at 350 Celsius? So we can convert it, we can transfer the data from this exponential to linear, right? To linear. Okay, it's an exponential function. You can take the natural log to transfer the data from exponential function to linear. Okay. Therefore, this is the linear function. We already mentioned previously, it's a linear function. Okay, it's the other linear function with different temperature. Is that clear? Okay, so we already know the temperature. The T1 is 300 Celsius, right? T1, and we know the diffusion coefficient at T1, right? And the question just asks the diffusion coefficient at T2, which is 350 Celsius, right? And we have to determine this coefficient, diffusion coefficient at T2, okay, at T2. Is that clear? Okay, so we just divided by nature log d2 over d1, right? We just divided by d2, d1. Okay, we got this, right? We got this, right? And this term equals to the nature log d2 minus nature log d1 and equals to this term. Okay, equal to this term. And then we can transfer this term. Okay, we can transfer this term, right? We transfer this data from exponential function to linear function. Of course, we can convert it, what? We can convert it back, right? We can convert it back to the exponential form. Okay, we can convert it, this term, this function to the exponential function here. Okay, and we already know what T1 and T2. T1 is 573 Kelvin and T2 is 623 Kelvin. Right, it's T1 and this is T2, right? And we already know T1 is here. This is the D1. Okay, therefore we can calculate the diffusion coefficient at T2. Okay, at T2. Right, and therefore we can figure out the coefficient of diffusion is doubled up than that of T1, right? Then that of that T1, then the diffusion coefficient at T1. Okay. And then let's look at the Fick's second law, which is describe the non-static state. The Fick's first law describes the static state. So the Fick's first law deal with the diffusion process that is independent of time. And the Fick's second law can handle with the diffusion process vary with time, right? Varying with time. Okay, so it's a partial differential. It's a PDE, partial differential equation, right? And this is the concentration rate per time, right? The concentration change, right? Concentration change. And the D is the diffusion coefficient, and this term is the what? Concentration gradient. Concentration gradient. Okay, it's a concentration gradient. Okay, when the atom want to diffuse through the host atom, we have to specify the boundary condition. Okay, the boundary condition. For example, we have certain boundary conditions. Like C naught, Cx, and Cs. The S means surface. Okay, the X means the certain distance inside the materials. And the C naught means the initial case, the initial concentration. Okay, initial concentration. Okay. And how to solve this partial differential equation? We have to use this called the error function. Okay, we have to use this error function here. Okay, it's a statistic function. It's called the error function in this term. Okay, in this term. I will show you an example how to deal with this function. Okay. And the solution of Fick's second law is applicable to only one set of boundary conditions. Other assumptions in the solution are the D is constant, the diffusion coefficient, and the surface concentration Cs of diffuse spaces is a constant. Okay, it's constant. Okay, and I want to show you one cases of this. For the copper diffuses into a bar of aluminum. Okay, this is the aluminum bar, right? It's aluminum bar, and this side is copper, right? We want to diffuse the copper into this aluminum bar, right? And what is its boundary condition? Its boundary condition is right here, right? It's here at this surface, right? At T equals to 0, that means this diffusion process doesn't occur, haven't started yet, right? That's mean the concentration is C0, right? The C0 means the existing concentration, the pre-existing concentration before diffusion occur. Okay, before diffusion occur, it's already certain amount of copper, right, inside this aluminum bar. Okay, and its range is from 0 to infinity. Right, 0 means the surface, infinity means the semi-infinite of this aluminum bar. So, and the T is greater than 0, that means the diffusion process occurs. Okay, and C equals to CS. CS is the surface concentration. Okay, it's the surface concentration at X equals to 0. Okay, and when the X equals to infinity, this concentration equals to C0, right? Equals to the pre-existing concentration of copper. Okay, and we can look at this figure, shows what? Shows the diffusion time, right? Shows the diffusion time. So as T equals to 0, that means we only have the this pre-existing concentration, right? Right? And its surface concentration is also constant. Okay, when this time the diffusion start, right? The time start to process, we can figure out what. We can figure out what. The longer diffusion time, the deeper depths of diffusion, right? The deeper, okay, the deeper depths of diffusion. Okay, so and the CS is a the C of X and T is the instantaneous concentration at location X. Okay, for example, I want to find the concentration of copper at X, this point, when the T equals to T3, right? Therefore, this concentration is CX T3, right? Right? Is that clear? And we can use this error function we already mentioned previously here to solve this equation, to solve this. Okay, and Cx is the concentration at certain specific point x at time equals to t, right? And the C0 means the pre-existing concentration. Cs is the surface concentration, right? It's a surface concentration, and the ERF is the error function. Okay, equals to this is a statistic function. Okay, and the error function values are given in a table. Okay, we can check the table and use the interpolation to find the value of z. Okay, the value of z. Okay. Okay, let's skip this. So give you an example is that an FCC iron carbon alloy initially containing 0.2 weight% of carbon is copperized at an elevated temperature and in a atmosphere that gives a surface carbon concentration constant at the 1 weight percent. If after 49.5 hours, the concentration of the carbon is about 0.35 weight percent at the position 4 millimeter below the surface, determine the temperature at which the treatment was carried out. Okay, so what is the pre-existing concentration C0? Right, is this right? 0.2 weight percent of carbon, because it's mentioned it's initially containing, right? So it's the C0. And what is the surface concentration? Here, a surface carbon concentrated is 1 weight percent, right? It's the surface concentration. Okay. Okay, so let's look at the solution of this problem. Okay. Therefore, the time is about 49.5 hours, and Cx is 0.35 weight percent, C0 is 0.2 weight percent, and the x is about 4 times 10 to the minus 3 meter, and the surface concentration is 1 weight percent. Therefore, we can plug those data into right here, the left-hand side, and we can plug in those numbers here, right? And we calculate it, and we move this term to the left-hand side, right? And we move this term to the right-hand side. Okay, and then we can find out the error function of z is 0.8125. Okay. Okay, and we use the interpolation to figure out the z value. Okay, we use the interpolation. We can check the table. When z equals to 0.9. When the error function of z, the value of the error function is 0.797, and the z value is about 0.9, and with the value of the error function is 0.8209, and the z value is about the 0.95. And after calculation, we know that the error function of z in our cases is 0.8125, and we don't know z. Z is unknown here. Therefore, we can use the interpolation process to figure out the value of z. Okay, value of z. And we can use the z value to solve the diffusion coefficient, right? Z equals to x divided by 2 times square root of d times d, t, right? And we can calculate the diffusion coefficient equals to what? X squared divided by 4 times z squared times t. Is that clear? And we plug in those numbers. We already know the depths. The depth after diffusion is what? Here. The depth is 4 millimeter, right? It's 4 millimeter. Right? It's 4 millimeter, and the z is 0.93. We already calculated from interpolation, and the time for diffusion is 49.5 hours, right? And we can calculate its diffusion coefficient equals to 2.6 times 10 to minus 11 meter square per second. Okay, meter square per second. And then to solve for the temperature at which diffusion coefficient we already have the above value, we use the rearrange. We use a rearrange form of this equation. Okay. Right, d equals to d naught per exponent, right? Exponential function, what? Minus q over rt. right? Do you remember this? It's D, right? We just rearrange to this form. Okay, we already know that D naught, this pre-exponent is a constant for the diffusion of carbon atom in FCC iron. Is about 2.3 times 10 to minus 5 meter cube per meter squared per second. And the activation energy to trigger this diffusion of carbon in FCC iron is what? Is right? Is this 148,000 joule per mole. And we plug this number, right, to here and here. And we can solve the temperature, right? The temperature T here. Temperature T here. Okay, so the temperature is about like 1027 Celsius. Okay, that means the temperature, the elevated temperature, determine the temperature, right? Determine the temperature. Therefore, the temperature is about 1027 Celsius. Right? So this iron, this FCC iron carbon alloy is heat treated at this 1027 Celsius for 49.5 hours. Okay, to carbonize its surface. Okay, to carbonize its surface. Okay, we'll just give you a brief introduction of this diffusion process. Okay. So today's course will be ended here. See you next week.